Okay, let's take a look at this problem. Longest increasing path in a matrix. Give an increasing matrix, find the length of the longest increasing path. So for example, this matrix, the longest increasing path is 1, 2, 6, 9. The output is 4. For this matrix, the longest increasing path is 3, 4, 5, 6. So the output is 4. It's not a 2, 3, 4, 5. We are not allowed to go this direction. And we are not allowed to go out of the boundary. For this problem, the direct solution is DFS traversal starting at each vertex. We are looking for all the 4 directions if they are not out of boundary, and if they are increasing, we keep looking forward. For example, at this node, all the directions is not valid. At this node, the same thing at this node. There are 4 directions to explore. We need to explore both of them. After we explored both of them, we need to compare which path is longer in this case. They are the same length. Then we go to this node. There's 1 direction to explore. This node, 2 directions. We need to explore both directions. This node, no directions. This node, we have 1 direction to explore. That is 1, 2. For this node, we have 1, 2, 2 directions. We will explore this direction, and we could explore this direction too. So as you can see, the DFS plus backtracking is able to solve this problem. For each node, all we have to do is we iterate through all the 4 directions, and for each direction we calculate the longest path we can possibly go. And this is a backtracking problem. Let's consider the time complexity. The time complexity will be at each node. For example, at each node, there are possibly 3 directions to explore that could increasing. So for each node, we need to make this decision, which direction to explore. The total state we could have is like 3 power mn. So many states to explore for each starting node. And how many nodes we have? We have totally a mn node. This is our time complexity. It will be a large calculation. So instead of make that decision which direction to explore, we can use a memorization. For each position, we can make a mn matrix to store the longest increasing path we can possibly find at each location. So for example, this location, we know the longest path is 1. This is 1. This is 2 after we explore. And so when we reach this node, if we are exploring upward, we already stored this as 1, so we don't have to look around. We just return 1 directly. So next time, when we visit this node, the cost is 01. The same when we process this node, when we look up, we immediately return 2. So this time, when we revisit this node, the time complexity will be 1. And when we process this node, when we look left, this matrix return 3. And we know the answer. So by using MN matrix, we could cut this complexity down to MN, because this time each node only have to be processed. Each node only has to be processed once, and this is our complexity. We trade space MN for the performance. So let's start looking at the code. Here is a global variable. When we examine the matrix, we record the longest path we have ever seen. And this is our memorization. After we run the solve, we print out this longest path length. So this loop loops through each vertex in the matrix, and we run the DFS. Once we process the DFS, we put them into the memorization, and we update the max length. Let's look at the DFS. If we already processed this vertex before, we directly return from the cache. Otherwise, we explore 4 directions. Say, if all the 4 directions are not valid, right? If they are all not valid, then this node only have length 1. That's what we return. However, those 4 directions have to satisfy they are not out of boundary. They're not out of boundary. And it's increasing. In that case, we explore one of the direction. At each iteration, we explore one direction. We find the length, and we update the memorization for that new node. And we compare the tempo max if we find a new, bigger tempo max. Finally, we return that temp max. That is longest length plus the current node length. And then we can get the result. So this is solution, DFS. The backtracking is done in this loop. It's a implicit backtracking. After we done one direction, we go to another direction, and we use a memorization to reduce the time complexity.